Bismillahirrahmanirrahim. The next topic is stability. We'll find the stability using the transfer function. Stability analysis is very important because if our system is not stable, we cannot design our system, we cannot analyze our system. So the first step is always to find the stability. The three important factors for a control engineer is steady state response, transient response, and stability. When we consider the transient response, we'll find the transient response whether the system is underdamped, overdamped, and when we consider the steady state response, we find the steady state error. We'll find the steady state error in the next some lectures. And the third thing is the stability. But if the system is not stable, then we cannot consider either to improve the transient response or to find the steady state error. So it is very important that the system is stable. So first we will find the stability using the transfer function of the system. These are the topics we are going to cover. The first topic is the definition. Obviously, first we'll define what is the stability. Then we will see what is the stability in S domain and in time domain. And we see what is the relationship between the two domains, why we are using the two domains. We are using S domains and time domains. Usually we design in the S domain. We design our systems in the S domain by adjusting the values of poles and all these things and zeros, and we'll find the transfer function for the adjustment of these values. And our final decision is always based on the time response. So both are important. S domain is actually important for the design purpose. Time domain is important because for all the systems, all our final decisions are based on the time response. Then after observing the relationship between the time and S domain, we'll classify the stability, and then we'll find what are the methods to find the stability of our systems and what some special cases we will face while finding the stability. So these topics will cover in the coming lectures. We can define stability as a system is stable if its impulse response approaches zero as time approaches infinity. First we define the impulse. An impulse is a function which appears for a very short interval of time and it has a very high magnitude. And when we apply impulse as an input function, the corresponding response is called impulse response. So we define stability in terms of the impulse response, that when impulse response approaches zero after a long time, or ideally we say that as time approaches infinity. So if impulse response approaches zero, we say that the system is stable, or we can say that if the impulse response or the system actually comes back to its equilibrium position, then the system is stable. We can also define stability as a system is stable if every bounded input yields a bounded output, or in other words we can say that a system is unstable if bounded input yields an unbounded output. What are bounded inputs? Bounded inputs are actually those inputs whose magnitude are less than some finite positive value for all time. It means that bounded inputs have some finite value, or in other words we can say it has some finite value or doesn't have any infinity value. Similarly, for the bounded output, if the value is infinity, that is undefined, then we can say that the system is unstable. So it must always have some finite value. Obviously, if we have some infinite value, then it means that system is out of control, our output is out of control, and system is unstable. So a system is stable if bounded inputs yield a bounded output, or vice versa, that is unstable if bounded input yields an unbounded output. Now we see the stability in S domain. In the S plane, how we define the S plane? We have sigma, or the damping factor, on the real axis, and j omega, or the damped frequency, on the imaginary or y axis. We define stability that if sigma is negative or the value of sigma lies in the left half of the S plane, then the system will be stable. And if our poles lie in the right half of the S plane, that is sigma is positive, then we say that the system is unstable. And if our poles lie on the j omega axis, that is it has pure imaginary value, then we say that the system is marginally stable, or sometimes we say that it is marginally unstable. So if sigma I is less than 0 or negative, the root's value is sigma I is negative or less than value, we say that the system is stable. And if sigma is 0, we say that the system is marginally stable or marginally unstable. It actually corresponds to a sinusoid, pure sinusoid, which is actually undamped. And if sigma I is positive, we say that the system is unstable. And the general value of the root is sigma plus minus j omega. Obviously this sigma, if this sigma is negative, the real part of the root is negative, then we say that the system is stable. Otherwise, if this sigma is negative, we say that the system is unstable. So this is actually an example of the pole location in the S-plane. This is actually a conjugate pair of pole. It has negative real part and some imaginary part also. Obviously we may have different type of pole locations. Here in the above diagram we can see that the first point, it is actually a pole, a single pole with a negative real axis, on the negative real axis. This is 2 and 2 dash is a conjugate pair of poles with negative real part. S equals to 0 is at the origin, pole at the origin. 4 and 4 steric, this is actually pole, a conjugate pair of poles on the imaginary axis, and these two poles 5 and 5 is positive real pole, and it is actually a conjugate pair with a positive real part. This is also a conjugate pair of complex poles but with a negative real part, and this is actually a conjugate pair of poles with a positive real part. So these are different location of poles. So this is actually the stable region, that is the left hand side of the S-plane, and this is the unstable region. Now we'll see the stability in the time domain. So we have defined first that why we are saying that the S domain, the left hand side of the S domain is actually stable and the right hand side of the S domain is actually unstable. If you have remembered that when we solve the differential equation of the system, we say that when our pole is on the negative real axis, the corresponding response is actually exponential in nature. So what about e raised to the power plus m1t if m is the root, and what about e raised to the power minus m1t if we have root on the negative and positive real axis? If we have root on the negative real axis, the corresponding response will exponentially decaying. It means that the transient of the system is actually decaying and eventually dies to 0. So when the transients reaches 0 or the transients exponentially dying, and the system, after the transients die, the system will reach up to a steady state. And when system reach up to a steady state, we say that the system is stable. While when the poles are on the right hand side of the S-plane, that is on the positive real axis, the corresponding time response is e raised to the power plus sigma t. And for e raised to the power plus sigma t, the transients are actually increasing with time. And when the transients are increasing with time, system will not reach up to a steady state. And when system will not reach up to a steady state, we say that the system is not stable, it is unstable. So we say that when the poles lie on the right hand side of the S-plane, the corresponding time response represents an unstable system. And if we have poles lie on the j omega axis, then we say that the system is marginally stable system. It means that our transients are constant and we have oscillations in the output. We say the system is marginally stable, or sometimes we say that system is marginally unstable, because if we are going to design an integrator or an oscillator in which we place intentionally the poles on the j omega axis, then we say that the system is marginally stable, because we are actually going to design an oscillator or integrator. Otherwise, in any other case, If transients are not dying and we have a constant oscillation, we say that the system is unstable. So if it is our wish to have oscillations, then we say that the system is marginally stable. Otherwise, we consider it as unstable. So we say that this is actually this right hand side of the S-plane corresponds to the decaying transients. So the system is stable, and this right hand side of the S-plane corresponds to increasing transients. That's why system is unstable in this region. Again, we see here that for different location of poles we have different time responses. This is this transients are actually decaying for this location of pole, the first location of pole. This is a conjugate pair of pole. For this conjugate pole, we see that our transients are actually decreasing sinusoidally. Although it is decreasing, but it also have a sinusoidal portion. So we notice here that when we have an imaginary part in the root, we have some oscillatory part in the response. And when we have only real root, that is without an imaginary part, then we have only exponential part in the time response. So actually the real part of the root corresponds to the exponential response, and imaginary part of the root corresponds to the oscillatory response. But in all these cases, if the sigma is negative, that is we are actually lying in the left hand side of the S-plane, our system will remain stable. And when we have poles on the j omega axis like here or here, we say that we have only oscillations. We don't have any exponential part because we have no real part in the root. So for pure imaginary roots, we have constant oscillations. Obviously, the frequency is actually changing when we are increasing the value on the j omega axis. If we have at the origin, we will have this step response at this as the output, or the time response. And when we are in the right hand side of the S-plane, our transients are increasing. Again, we can see here that if it is on the real axis, transients are exponentially increasing. And if it is a complex conjugate pair of pole, that is, it has some imaginary part, then it has some oscillatory part also. Also, we notice here that for these two locations, the rate of decreasing the exponential is different. For example, if this is -2 and if this is -5, the rate is here is e raised to the power -2. The corresponding time response is e raised to the power -2. Here is e raised to the power -5. So in both cases, actually the rate of decay is different. Similarly, here in the right hand side of the S-plane, for example, if this is 2 and this is 5, then this is actually correspond to e raised to the power 2t, and this corresponds to e raised to the power 5t. So in both cases, the transients are increasing exponentially with a different rate. In general, if we have at this point, for example, -2, it is closer to the j omega axis, and the more it is closer to the j omega axis, the longer will it take for the transient response to die out. Now we see that we have seen in the previous slides the transient response either increasing or decreasing exponentially, or some increasing or decreasing with exponentially with some sinusoid for the complex conjugate of poles. But here we see that we are actually watching the corresponding step response. We have studied the transient response in the previous slides. Now in this we are actually observing the step response. So again, you see that this is actually the corresponds to point 1, that is negative real. We have pole on negative real axis. The system is actually reaching up to the steady state exponentially. When we were drawing these transients separately, we made it like that the transients are actually decreasing like this, but that is actually the transient response, and this is the step response. In this we have shown like this, that transients are increasing, which is actually decreasing, and system is actually reaching up to a steady state. So this is actually the step response. You can draw it using either MATLAB or manually, obviously. This is actually 2 and 2 dash is the pair of complex conjugate pole. So in this we have step response. The transients are actually decreasing exponentially and then reach up to a steady state. So finally you have a steady state position here in the step response. That's why we are saying that the system is stable. So here you are actually having a steady state value. Similarly here you also have some steady state value. That's why we are saying that the system is stable. Now if you have poles on the j omega axis like 4 4 dash, so you have pure oscillations. So we say that this is marginally stable. And in the right half of the S-plane, whether you are at 0.5, that is positive real pole, or you have complex conjugate pair of pole 6 6 dash with a positive real part. In both cases the system is actually not reaching up to a steady state. Here the transients are increasing with time and system is not reaching up to a steady state, so we are saying the system is unstable. Here in this case 6 6 dash, transients are actually exponentially increasing and system is never reached up to a steady state, that is system is unstable. So here again we say that the system is unstable. These are actually the step responses. Please keep in mind that while we were drawing these type of transients, whether exponentially decreasing or increasing, we say that these transients are actually decreasing with the time and eventually decays to zero, and system will reach up to a steady state. And these are the step response, that when we have applied step function as an input, then we will get these types of step responses for the system. Now here we have seen this in detail in the previous slides. The only thing is that when we have complex conjugate pair of pole or we have simple real pole, we have different types of responses for the stable systems. Response could be underdamped, critically damped and overdamped. I think we have already discussed in detail in the previous lectures that for complex conjugate pair system is stable with underdamped response, and for unique and negative poles on the real axis we have critically damped and we have overdamped on the real axis. We have critically damped for the repeated roots or repeated poles for the critically damped and unique for the overdamped response. Now here we see actually that these are the transients which is actually enveloped in an exponential function. This is actually correspond to a complex conjugate pair. Here actually what I want to show that these stable systems have oscillatory transients which are actually enveloped in the exponential function. So this is an exponential function, and this is corresponds to this. These transients are actually enveloped in the exponential function and the system will finally reach up to a stable state. So here you can draw it like that. This is the exponential function. This is actually making an envelope, and this is for the complex conjugate pair. This is e raised to the power sigma t plus both for both pairs. We have two lines here. One is exponentially decreasing here, and this is for the complex conjugate pair, and eventually it is making an envelope and oscillations will remain under this envelope. Similarly here exponentially, for the exponentially increasing transients, the oscillatory part is actually increasing and system is unstable. Now we classify the stability as either absolute stability or relative stability. Absolute stability is actually the question of simply yes or no, not yes or no, that whether your system is stable or unstable. So we can find absolute stability and it will give us just the answer of stability, yes or no, that whether our system is stable or not. Whereas relative stability is actually the degree of stability, that if your system, once your system is found to be stable, if it of interest to know, to determine that how much stable it is, or we can say in other words that how much it is close to be being unstable. Relative stability actually tells us that how much it is close to be being unstable. This is actually a concept of the relative stability. Usually relative stability is expressed in terms of some allowable variation of a particular system parameter. So if we allow to vary some particular system parameter, then system should remain stable. This is actually the concept of relative stability. So we can classify stability as whether it is absolutely stable or relatively stable. We have some methods to find the absolute stability, that is Raoult stability criteria or Havertz stability criteria. We'll discuss in details in this lecture later on. And we'll find some ranges of the parameter also to find the relative stability, that for some particular parameter what is the range that if we change the value in that range, system should remain stable. We'll see this in later in this lecture. This is an example. This is quite obvious from the previous discussion, that if we find the roots of the characteristic equation, we can simply tell if it is it lies in the left hand side of the S-plane, it is representing a stable system, and if it lies in the right hand side of the S-plane, system is unstable. But sometimes for higher order systems it is difficult to find the roots. For example, if you have a 23rd order system for an aeroplane, or if you have more higher order systems, then sometimes it is usually difficult to find the roots. So we have some other methods. Without finding the roots of the characteristic equation, we can find the stability. Here is an example. In the first part we see that this is the block diagram of the system, which have forward transfer function as 3 upon s plus 1, s plus 2, and when we simplify this and we find the closed loop transfer function using g upon 1 plus gh, we have discussed in the block diagram part of the lectures. We use g upon 1 plus gh to find the closed loop transfer function, and our closed loop pose actually lies here in the left hand side of the S-plane, and its corresponding time response is this. Obviously we have a conjugate pair of poles here, so we are actually our transients are actually varying exponentially and oscillatory both in nature, and finally reaching up to a steady state. And for the same location of poles, if we change the value of gain from 3 to 7, our closed loop poles, again we use the same formula g upon 1 plus gh, again for the same s denominator s plus 1 s plus 2, when we find the closed loop poles, our loop is actually changed from this position from this position, that is from the left hand side of the S-plane to right hand side of the S-plane, and system will become unstable. So we see here that while changing the value of gain, system will become unstable. So sometimes it is very important to find range of some parameter to find the range for the stability. So we'll see it later on that how we'll find the range of some parameter that such that the system will remain stable. Now we'll see a method to find the stability of the system. This is the Raoult stability criteria. The Raoult stability criteria tells us about the absolute stability of the system. Absolute stability of the system is actually the system is stability in terms of the answer yes or no. So it just gives us about whether the system is stable or unstable, and it actually tells about the absolute stability without actually solving for the roots of the characteristic equation. As we know that for higher order systems, for example, if we have a 22nd order system, then it will be difficult to find the roots of the characteristic equation. So it is desirable to have a method in which we can find the absolute stability of the system without actually solving for the roots of the characteristic equation. So this method actually gives us the stability without solving roots. It also tells us the number of roots with positive real parts. Actually, the roots with the positive real parts causes instability in the system. So it tells us about the number of roots with the positive real parts which are actually causing the system to be unstable. This method gives necessary and sufficient condition for all roots of the characteristic equation that lie in the left half of the S-plane. It is a condition that if all the coefficients of the characteristic equation are positive and all powers of s from s raised to the power n to s raised to the power 0, that is from the highest order present in the characteristic equation up to s raised to the power 0 or a constant term, are present in the characteristic equation, then the system will be stable. This is a necessary condition but not sufficient. Even sometimes with these conditions, system is unstable. So this criteria actually gives sufficient and necessary conditions for the system to be stable. So we'll see how we'll apply this formula. What are the limitations of Routh stability criteria, or it is also called Routh? First, we have to make a Routh-Hurwitz table to find the stability. We have some limitations for this method. This is actually the characteristic equation that is sometimes represented by A of S, that is auxiliary equation, or the characteristic equation Q of S. Highest power of S is S raised to the power n, and the second is S raised to the power n minus 1. It is in decreasing order of decreasing power of S raised to the power n minus 2, S raised to the power n minus 3, and then up to S raised to the power 1, S raised to the power 0. And the corresponding coefficient of s raised to the power n is a n, corresponding coefficient of s raised to the power n minus 1 is a n minus 1, and so on. So this is actually the standard form of the characteristic equation of the system. To make a Routh table, first we have seen the characteristic, we should see the characteristic equation, and if a naught term is 0, then we'll divide the whole equation by s to get it in this form, in the standard form. On all a's should be real coefficient, and all powers of s from s raised to the power n to s raised to the power 0 must be present. So this is actually the limitation before applying the Routh-Hurwitz table. We'll make a Routh table by using the coefficient of the characteristic equation. The first two rows of the Routh table will be filled by using the coefficient of the characteristic equation. We'll start the first column at the left hand side from the highest power of s. In this general equation, s raised to the power n is the highest power, so we'll start with the s raised to the power n. The first is s raised to the power n, then s raised to the power n minus 1, that is the decreasing power of s, and we'll go up to s raised to the power 0. To make the table, first we'll write the left column from the highest power of s raised to the power n, to s raised to the power n minus 1, s raised to the power n minus 2, and so on. And then we'll fill these rows by using the coefficients of s raised to the power n, s raised to the power n minus 1, that is the coefficients from the characteristic equation. For the first row corresponding to s raised to the power n, the first coefficient is an, then we will write the alternate coefficients. An, then an minus 2, then an minus 4, and so on. So it depends on the power of s, how many coefficients we will have in the first row. For the second row, s raised to the power n minus 1, the coefficient of s raised to the power n minus 1 is an minus 1, and then we have written here the alternate coefficients. So the first two rows of the Routh table are actually completed with the help of the coefficients of the characteristic equation. Next, the remaining table we will compute by using the coefficients, and we'll fill this table. For the next rows, that is third, fourth, and so on, next rows, we calculate B1 as, we first multiply an minus 1 by an minus 2, and then subtract the product of an and an minus 3 from this, and we will divide by an minus 1. For all the values in the third row, we will divide by the first element of the just preceding row of that row. For example, for the third row, for all the values b1, b2, b3, we divide by first element, that is an minus 1 of the previous row. For the fourth row, c1, c2, c3, we will divide all the values by the first element of the previous row, that is b1. So here you can see that we have divided by b1 for all these terms. So we'll calculate b1 as an minus 1 into an minus 2 minus an into an minus 3 upon an minus 1. Similarly, we calculate b1 an minus 2 multiply by an minus 4 minus an into an minus 5 upon again divide by an minus 1, and so on. We'll calculate all these terms in the similar manner. To calculate b2, we will use first column of the previous two rows and the column next to the term b2. We'll use these two columns. To calculate b1, we will use these two columns, the first and the next to this. To calculate b2, we will use the first column and the column next to this. If we use, for example, b3, to calculate b3, we will use first column and the column next to this. Obviously, we don't have written some values here, but we'll use these two columns if we calculate b3. Similarly, for c1, we will use the previous two rows, first column and the next column to the c1. So we'll use these two columns. To calculate c2, we will use the previous two rows and the first column and this a3 into an minus 5, the next column. Similarly, to calculate c3, we'll use the previous two rows, first column and the column here, this one. If we'll have this one. So we have calculated the route table. Now we see that what is the criteria, that how we find the stability from this route table. The criteria is that if all the roots of the characteristic equation have negative real parts, if and only if the elements of the first column of the route table have the same sign. It means that the first column of the route table, that is these terms, that is the first column of the route table, have the same signs, then the system will be stable. If there is a sign change in the first column, then we say that the system is unstable. And the number of times the sign changes represents the number of poles on the right hand side of the S-plane. So if we have two sign changes, it means that we have two poles in the right hand side of the S-plane, and system obviously will be unstable. So this is a method to find the stability from the route table, that if all the elements in the first column of the route table have the same sign, then the system will be stable. This is an example of the sixth order characteristic equation. Then how we'll calculate the third, fourth and so on next rows using the coefficients of the characteristic equation. So because we have here the sixth order, so we'll start with the highest power of s raised to the power x, s raised to the power 6, and then we are actually having here the decreasing power of s raised to the power 6, s raised to the power 5, s raised to the power 4, 3, 2, 1 up to 0. The first two rows are actually calculated with the help of the coefficients of the characteristic equation. The coefficient of s raised to the power is the coefficient of s raised to the power 6 is a6. So we have first written here a6, and then we have written here the alternate powers. So a6, a4, a2, it will go up to a0. For s raised to the power 5 or second row, first we have written here the coefficient of s raised to the power 5. Then we have written here the alternate coefficients. It will go up to a1, a5, a3, a1. And then we have nothing coefficient to write here as the coefficient, as there no more coefficient. So we have written here 0. Now the third row, for the calculation of third row, we will use the first row and we'll use the next row to the entry which we are going to calculate. So here we are going to calculate the first entry of the s raised to the power 4. So we are using first and second column. This is again a raised to a5 minus a5 multiplied by a4 minus a3 a6 divided by the a5, the first element of the first column of the previous column. Sorry, the first element of the previous row. Now for B, we'll use the first column and the column next to this entry. We are using these two columns, but all the time we'll divide with the element of the row just preceding the row of s raised to the power 4. So we always divide by a5. So a5 into a2 minus a6 into a1 divided by a5. Similarly, we can calculate this entry, we can calculate this. So here we have actually a 0, so we'll use two columns, always the first column and the next column. So a5 into a0 minus a6 into 0, because there is a 0 here, divided by again a5. This term will become 0 because it is a6 is multiplied by 0, and a5 will be cancelled, so the result is a0. Similarly, we can complete this route table in this fashion, using always using the previous two rows, that is a3 minus a5b divided by a. And we always divide by the element of the first element of the previous row to calculate the next row. So here we always divide by capital A, here we always divide by capital C, and we'll complete this route table up to s raised to the power 0. So this is the complete route table. Now we'll see first example. Make the route table for the system shown in the given figure. Obviously, make the route table, we are making the route table, but ultimately we are going to find that whether the system is stable or unstable. So this is a system with a unity feedback, that is here h of s is equals to 1, and the forward path transfer function is 1000 upon s plus 2, s plus 3, s plus 5. So first we find the closed loop transfer function. So we have solved this using the closed loop transfer function. The relationship of the closed loop transfer function, that is C upon R equals to G upon 1 plus GH. We have discussed in the block diagram portion of the lectures, and we have found it as 1000 upon s cube plus 10s square plus 31s plus 1030. So this is the characteristic equation, s cube plus 10s square plus 31s plus 1000. Now for the characteristic equation of this system, first we will make the route table. This is the third order equation, so we'll start with s cube, and first we write s cube, then the decreasing power of s square, then again s square. We'll see what we have done here. S raised to the power 1 s naught. The first two rows are actually filled by the coefficients of the characteristic equation. So the coefficient of s cube is 1 and the alternate coefficient is 31, and then there is no other coefficient, so we have put a 0 here. The coefficient of s square is 10 and the alternate coefficient is 1030, and there is no term alternate power available in this equation, so we have put a 0 here. We can apply any row operation in the route table. So we have divided this row of s square by 10. We can have division or multiplication operation. We can say just multiply by 1 upon 10 just to simplify the route table. And it is important that we will not multiply it by a negative constant, because if we change the sign, the result obtained from the route table may be changed. That's why we simply divided by 10, and the simplified row is 1. 10 divided by 10 is 1. 1030 divided by 10 is 103. So next we will use this row, the first row of s cube and the third row of s square. We will not use the second term of s square, second row of s square. Although we can use it also, but it will make only the calculations larger. So we can simplify it by dividing it by 10. Then we fill the next row, and we multiply 1 by 31 minus 1 multiplied by 103 divided by 1, and this is equal to minus 72. Then we use here 1 multiplied by 0 minus 1 multiplied by 0. We use the first column and the column next to this entry, because here are all zeros, so we have a 0 here. Similarly, we fill this s raised to the power 0 row, minus 72 multiplied by 103 minus 1 multiplied by 0 divided by minus 72. The result is 103. So here we see that there is a sign change in the first column. We have completed the route table, and we see here that we have a sign change in the first column. Sign change means that the system is unstable. We can see here clearly that there are two sign changes in the first column. From s square row, it is plus 1 in the first column, and in the s raised to the power 1 row, this is minus 72. There is a sign change from positive 1 to minus 72. And then in the s raised to the power 0 row, it is plus 103. So again there is a sign change from minus 72 to plus 103. So it means there are two sign changes in the first column, from positive to negative, and then again from negative to positive. So it means if there are two sign changes in the first column, it means that there are two roots which lie in the right half of the S plane. So there are two roots with positive real parts, and we concluded that the system is unstable. Now we'll see another example. Find the stability of the control system. Having the characteristic equation s raised to the power s plus 3s cube plus 3s square plus 2s plus 1 equals to 0. Obviously, we'll make route table to find the stability of the system. We'll start with s raised to the power 4, as the highest power of s in the characteristic equation is s4. So we have started with s raised to the power 4 in the extreme left column. Then the decreasing power of s is s cube, s square, s raised to the power 1 and s raised to the power 0. We have filled the first two rows by using the coefficients of the characteristic equation. So we use the coefficient of s raised to the power 1, which is 1. Then we use the alternate coefficient. So the third one is the coefficient of s square is 3. We have put 3 here. Then next alternate coefficient is 1. We have put a 1 here. Then the coefficient of s cube is 3, so we have written 3 in the second column. The next alternate coefficient is s2s, so we have written 2 here. So in the first column we have written the coefficient of s raised to the power 4, s square and s raised to the power 0. In the second row we have written the coefficients of s cube, s raised to the power 1, and there is no third term here to write. So we have just left it blank, or we can put a 0 here. Both have the same meaning. Then we have filled the third column by using the formula we use. So this is 3 multiplied by 3 is 9 minus 2 multiplied by 1 divided by 3. Again we have used the first element, and this is equal to 7 upon 3. Here we use the first column, that is 1 and 3, and this the next column to this term. So this is 3 multiplied by 1 minus 0 multiplied by 1. Here actually we have assumed that there is a 0 over here, divided by again the first element. So it is 3, so it will become 3 upon 3, that is equal to 1. For the next row, we will multiply 7 upon 3 multiplied by 2 minus 3 multiplied by 1 upon 7 upon 3, and when we simplify this term, it will be 5 upon 7. And next, we will multiply 5 upon 7 multiplied by 1 minus 7 upon 3 multiplied by 0. Obviously, we assume that there is a 0 here. So it will be equal to 1. So we see here that there is no sign change in the first column. It means that the system is stable, and we conclude here that this system is stable. This is another example. Find the stability of the control system having characteristic equation 2s to the power 4 plus s cube plus 3s square plus 5s plus 10. We can see easily that we have used the highest power of s and then decreasing power of s in the first column to fill the route table. Then we have used the alternate coefficients. The first is s to the power 4, so the coefficient is 2. The alternate is s squared, coefficient is 3, then 10, and then the coefficient here is 1, and the alternate is 5. So we have filled the first two rows by using the coefficients, and then we have calculated the remaining in the same fashion we have discussed in detail in the previous examples. So 1 into 3 minus 5 into 2 upon 1 is minus 7, that is 3 minus 10 is minus 7. 1 into 10 minus 2 into 0 is 10, and then we have solved 7 minus 7 into 5 minus 10 upon minus 7. This will 6.430, and this is 6.43 multiplied by 10 minus 0 multiplied by minus 7 upon 6.743. So answer will be 10. So we can see here that there are some sign changes in the first column from 1, positive 1 to minus 7, and then minus 7 to plus 6.43. It means that we have two sign changes in the first column of the route table. It means that the system is unstable with two roots in the right hand side of the S-plane. If we solve the equation, we will see that for the fourth order equation, we will have four roots. The two roots are at s equals to minus 1.005 plus minus j.933. So for these two roots, actually we have negative real part, but for the remaining two roots, s equals to 0.755 plus minus j1.44. so here we have two roots with the positive real parts. All the roots are actually in complex conjugate form. So it is clear from here that although there is no power of s is missing, all the coefficients are positive, but the system is unstable. So we use route table to find the stability of the system, and we have found here that the system is unstable with two sign changes, that is two roots lie in the right half of the S plane. So this is how we find the stability from the route table.